Okay, G. Let's start with a new topic. And the topic is constraint satisfaction problem. So, constraint means condition. Uh, so, constraint satisfaction problem is a kind of problems in which we have to fulfill some conditions, some constraints. So, generally, in a constraint satisfaction problem or CSP, these are the problems in which we have to satisfy some constraints. So just a more formal definition to understand the CSP is that in these kinds of problems, we are given with a problem, and then we have to identify from that problem the first that what are the variables in it. So then we have to identify the set of values, and then we have to assign those values to these variables by considering the available conditions or by considering available constraints. And if when we will assign these values to these variables by satisfying all constraints, then finally we can say that our problem is solved, and this is a form of the constraint satisfaction problems. So to solve this constraint satisfaction problem, we have to use some factored representation. Factored mean we have to divide the problem into different forms, and those forms are called factors. And the first factor, for example, you can say is the set of variables that you have to identify. And then the second factor is the set of domain, which will contain the values that you have to assign to the variables lying in the set of variables. And then finally, you will have to identify from the problem that what is the set of constraints that is containing different conditions or constraints that you have to look over. And then after looking over that, you have to assign the values from the set of domain to the variables, and in this way we can go on. So this is a factor representations. So let's move on to more formal definition of constraint satisfaction problems. So in a constraint satisfaction problem, we have to divide the problem in three components. The first component is X, the second component is D, and the third component is C. So the X is a set of X. Here you can see on the slides, and I am moving my cursor. So X is a set of variables, and therefore it's a set of variable, and it can contain x1 to xn different variables. And then D is a set of domains, the D is a set of values, and these values can be from V1 to Vn or from D1 to Dn, and these values we have to assign to each variable. And then finally we have a set of constraint that's called C, and we have to, when we will assign some value to the variable, then we will see these constraints, and then we have to keep in our mind that all the constraints must satisfy if we want to solve our CSP. So C is a set of constraints that will have allowable combination of, that will allow the combination of values to the variables. So this is the factor representation. And now one person can ask you that represent all your constraints or present all your conditions or constraints, then we have some formal definition. And that formal definition to represent the constraints is just like this one as written here, scope, comma, rel. Rel is for relation. So you have to write a constraint, a single constraint in a form of scope, comma, relation pair. and you have to write within the angle brackets. These angle brackets are not necessary. You have other short notations to represent your constraints as you normally do in your mathematics. So this is here we have a freedom and representation of constraints, you can say. So what is scope and what is relation? This question is still remaining to understand this pair of scope comma relation. So scope is a tuple of variables. So scope is a record of variables that and so we can understand that in this tuple or in this record, we will have to represent some variables. And which variables? The variables that are participating in the constraints. So are the variables that you are dealing with currently. You have to mention those variables here in place of scope. And then there is a relation. So relation is again, you have to represent the relation between the variables that you have mentioned in place of scope. So you have to represent the relation between those variables, the condition between those variables. So you have to represent that condition, that constraint here at this part, which is mentioned by rel or relation. To understand this concept further, there's an example given here at the bottom of this slide. And suppose we have two variables, x1 and x2, and the values, the domain values are the set of domain for these variable is a and b. So a and b are the values for these variables x1 and x2. We want to assign these variables, we want to assign these values to these variables, but there is a constraint that x1 and x2 would not have the same values. So it means that if we are going to assign value a to x1, then we cannot assign this value at the same time to the variable x2. And similarly, if we are going to assign the value b to variable x1, then we cannot assign this values in the same time to variable x2. So variable x1 and x2 must have different values. So this is the constraint. So there are two representations mentioned here at the last line of this slide. First representation is very much complex and not easy to understand, and the second one is very much close to the mathematics and normally the people will understand these things quite easily. So, so for example, here in this angle brackets, we have, this is the scope, and this part is called the relation part, which is starting from this square brackets to this square bracket. So in the first part, we have two variables x1 comma x2. So this is called scope, and in scope we have to represent, or we have to write only the variable. So that's why it's okay. And then the second part is the relation, in which we know that we have to mention the relation between the values of the two variables. So here this part is saying that here, for example, the first part of this part is containing a comma b within the parenthesis, and then it means that this a is for x1 and this b is for x2. So it means that if a is going to assign to the variable x1, then b is going to assign to the variable x2. And similarly, if we are going to assign b to x1, then a is going to be assigned to the variable x2. So this is very much clear that here in this representation, x1 and x2 must have different values. And similarly, in the second representation, this is the first part that is called scope, and this is the second part that is called relation. And in the scope part, we are writing, or we are mentioning only two variables, x1 and x2, which is quite clear. As I said, that scope is a part in which we have to write the variables. And then in the second part, which is relation, And here we have to mention the relation between the variables or between the values of the variables. So you can write values here, or you can write directly variables, and then you can represent the relation. This is the relation. This is relation not equal. This not equal is basically the relation, is basically the constraint, so which is giving you the concept that x1 not equal to x2, and it is quite clear that there are two variables involved in this pair, and both the variables have different values. So it is clear. Even we are not mentioning the values here a and b, but it is clear mathematically that x1 is not equal to x2. So this is also the form to represent these pairs of constraints, or you can simply say that this is the form to represent constraints. So now, moving on, just a minute. So moving on to this slide and defining CSP further, first thing that we have to know that if we want to solve a CSP, then the first thing that we have to understand our state space. We have to define our state space. State space means already, for example, if you just remind that example of Romania that we studied in chapter 3 of searching during informed and uninformed searches, then you normally see, for example, all states in a space is called state space. So this is the simple definition to understand, but I hope that you have the understanding of state space. So this is the space in which you normally consider all the states, all the variables, all the things generally involved in your problem. And when you are considering all states, variables, things involved in your problem, then that is your basically state space. So if we want to solve a CSP, then the first thing that we have to understand our state space, we have to define our state space, and we have to define some kind of a notion for our solution. And what is that notion? 3 divisions: the variable x, or set of variables that is called x, set of domain values that is called d, and the third is the set of constraints. So you have to define these things first before going on to solve your problem. So anyhow, then the next step after defining your state space and building some notion, then the second step, you have to assign, this is mentioned here in point number 2 on the slide. So the second step that you have to do is to assign values to the variables that you have. We have variables, for example, x1, x2, x3 in our variable set x, and we have domain values in set d. So we have to pick some value from the set of d, and then we have to assign in the towards some variables by selecting that variable from the set of variables. So just a minute. Okay, coming back to our presentation, our lecture. So sorry for the disturbance. When you are at a home, so these kinds of disturbances always there. So anyhow, no issue. Let's continue. And we were discussing something at point number 2 on this slide. So the second step is that we have to assign values to the variables, and values are lying in the set of domain values, that is D, and variables are lying in another set that is called X. So it is simple. So we can assign some value Vi to some variable Xi. We can assign some value Vj to some variable Xj, and so on. So we have to assign these values by considering what? By considering the constraints that are available in our constraint set. So let's keep this thing aside and let's try to understand some other general terms. So one general term in this area of CSP is called legal assignment or consistent assignment. So what is this one, legal assignment and consistent assignment? So when you normally assign some value to some variable, and if you are assigning this value to some variable and there is no any violation of the constraints available in the constraint set, then it is called legal assignment, that it is called consistent assignment. So that's all for the legal assignment. So this is the definition of legal assignment. So if you are doing something, you are assigning some value to some variable without violating anything. Anything is lying in yours another set that is called the set of constraints. So without violating anything, without violating any constraint, when you assign some value to some variable, that is called legal assignment or consistent assignment. And the other definition in the next point is called complete assignment. So what is complete assignment? So complete assignment is a concept, overall concept. So for example, you have a problem, and in your problem you are assigning variables, you are assigning values to the variables one by one. You are assigning these values, and if you have 5 variables and you have assigned these variables with the values, and if your all assignments are consistent and you are finished with your assignments, then that is called complete assignment. That is called, you can call it complete assignments, but the last one, if all previous 4 were consistent and you are performing this last one and this last one is also consistent, then you can say that this is the complete assignment. And finally, it is the partial assignment. That is very much clear that if this is the problem for 5 variables and you are just doing with the third variable or the second variable, and rest of the variables are still remaining and you have to assign the values to these variables yet, but at the moment you are performing second or third, so that is your partial assignment. You are in between the process, so that is your partial assignments. Here in partial assignment, we are not talking about consistent or legal or whatever. This is something, the partial process. That process is not complete yet. So that is called partial assignment. So let's move on to the example. And this example is about map coloring. And we have a very much traditional map from the textbook. And this map is, the map that we have here is of a country, and that country is Australia, very much famous and well known. So these are the, so for example here, this is the map. If you will look on to your slides, this is the map, and we have different states available in this map. One state, which is Tasmania, is not joining with any other state. It is some kind of independent state, or you can say it is some kind of a separate state in the map. So there is no neighborhood between this Tasmania and some other state. There is no direct connection. So maybe there is a sea between it. So on the right hand side, you are seeing a graph. This graph is called constraint graph. Constraint graph is what? Again, the same constraint. Okay, I will come to this point later on. But first, if this is our problem, and in this problem we have to color the states available in this map, and these are the states: Western Australia, Northern Territory, South Australia, Queensland. All these are states, and we have to color this map with respect to states, and this is our problem, that we have to color the states. So these states available in the map are variable then. So we have to define the set of variable as Western Australia, Northern Territory, comma, Queensland, comma, New South Wales, comma, Victoria, comma, South Australia, comma, Tasmania. So this is the set available to us to solve this problem of CSP. And then, and what are the colors available to assign to these states? That is also given in our problem statement, that is given in the textbook in a theoretical form. And we can infer from that text that the set of domain values D is only containing 3 colors, red, green, and blue. So this is another set of colors that we have to assign to these states, NT, NSW, and so on and so on. So this is your second set, which is containing the values. And from that text, which is available on the textbook, you have to infer, again, we can infer from that textbook that we have some constraints available there. And the constraints available in that problem, our case study is, we cannot assign same color to neighbors. For example, Western Australia and South Australia are the neighbors. So we cannot assign same color blue here and blue here. No, it is not possible. Maybe we can assign blue here and we can assign green here. And then if, for example, these are also the neighbors, these are also the neighbors, these are also the neighbors. So we have to consider all these constraints. And by considering all these constraints, we have to color this map. And the constraint is that each neighbors must have different colors. This is the constraint. It is written here, neighboring regions to have distinct colors, which means neighbors must have different colors. So this is our constraints. So, and this is our first step of factorization. So this is your factorization. And now, before solving your CSP, it is always a good step to form a constraint graph first. So you have to build some kind of a graph. You have to build some kind of a graph or graph by considering the constraints available to you. So my constraints in this problem is that neighbors must have different colors. So we have to, so constraint is what? Our constraint is neighbors. So then we can draw a graph that WA, Western Australia, is a neighbor of NT. We can infer this neighborhood from this map. WA is a neighbor of South Australia. South Australia is a neighbor of NT. SA is a neighbor of Queensland, and so on. So these lines these links are representing the neighborhood between different states. And this Tasmania is again representing itself as a separate state and not linked with any state here. So let's move on to the next slide. This first point is saying the same thing which I already told you, that you have to build some constraint graph. And this constraint graph is always a helpful tool if you are going to solve your CSP. So, and if you will look over this constraint graph, then the links available here are the links that we have introduced here are 9 in number. So these are total 9 links. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 links. And there is no link between Tasmania and any other state, because this Tasmania is a separate state and there is no neighborhood available here according to this map. So it's clear. So now if somebody will ask me, represent all your constraints into the form of scope, comma, relation, then how can I represent these? So here you can see C is a set of constraints, and in this way you can write something between these curly brackets. So SA not equal to WA. So this is according to this one, SA not equal to WA. SA not equal to SA not equal to NT, SA not equal to Queensland, SA not equal to NSW, SA not equal to Victoria, and in this way, and for example, Victoria not equal to NSW, and NSW not equal to Q, and NT not equal to Q, and so on. So these are the 9 links or constraints are available that you can now write here in this set C. So that was something, a theoretical representation, and this is something, a mathematical representation. So uh, the next point is just giving you uh, an idea that how you can evaluate different values to different variables, and only the case of SA versus VAR is given here in this point. So SA not equal to VAR, we know that it's not a different thing. It's a short notation that we already studied here in this, on this slide, scope comma rel. This is something very formal, and this is something very informal and very much close to the mathematics. So anyhow, this is not an issue. You can write in your own way. This is not an issue. Just like algorithms. So SA not equal to what? So this one, SA not equal to var, is a shortcut representation, is a shortcut of its formal representation. And what is formal representation? We know that that is into the form of scope, comma, relation, and then we can write these things in between angle brackets. Like this one, SA comma var, and then comma SA not equal to var, and then this is something between angle brackets. So if I will ask that what would be the possible colors for these two states, then what would be your answer according to the constraints that are available to you? We have 3 colors, red, green, blue. So what you can do, you can assign one color, for example, red to SA, and then you can assign the remaining 2 colors to the VAR actually. For example, here, if you will assign red to SA, then the possible color for the VAR is green. And again, if SA is red, then the other possible color is blue. And that's the end for this possibility when you will assign the red color to SA. Similarly, if you will assign green to SA or SAW, then red is available for VAR. And if you assign green to SA, then blue is available for the VAR. And similarly, if you will assign blue to SA, then red and green are available for the WA. So these are the possibilities, or these are the enumerations that are available only for this pair. And in this way, you have to check manually first. I'm not talking about algorithm. If you are writing algorithm, then you have to check through algorithmically that what are the possible colors available to assign to these neighbors. Sorry. So in this way, you can assign different colors to different states, and you can go on with all the neighbors, and finally you will have your solutions in your hands. And for this problem, there are more than one solution, and one solution is given here. And you can assign VAR red, NT green, Q red, NSW green, V red, SA blue, T red. This is one solution. So this is the representation of the solution. You can represent or write a solution in this form, or you can write your solution figuratively as you are seeing here. So for example, if SA is blue, then all these are the neighbors, and you are seeing that these neighbors have different color, these neighbors have different colors, these neighbors have different color. Similarly, this one. And similarly, you can check the neighborhood among these one. For example, VAW, NA different, NTQ different, Q, NSW different, NSW Victoria different. And here you are free to give any color because it is independent. So when you will check these possibilities, there are two approaches. The first approach is a brute force approach, in which you have to check all the possibilities one by one, and you will not leave even a single option. You will not leave it. You will not leave it behind. You have to check all the possible options for assigning colors to different states. And the other option after reading this topic is that you can use this CSP. Approach. So the difference between the normal brute force approach and the CSP approach is just given here on this slide at the bottom, and only one case is represented here and it is that if you have the state SA, and if you will assign this SA a blue color, and then how many neighbors of this state? 1, 2, 3, 4, 5. 5 neighbors. And how many colors available in our domain, set of domain? 3 colors: red, green, blue. So we have a formula, and by using that formula, you can calculate how many number of assignments that your algorithm has to check only for this state. So for example, 3 is the number of color, 3 colors, and then raised power 5. So there is something, these 5 states, 1, 2, 3, 4, 5. So 3 raised power 5, we have 243 assignments that we have to check in case of this essay, when you are going to assign this blue color to this essay. This is brute force. But if you will use CSP approach, then you don't have to use 3 raised power 5, because in case of SA, we are already assigning this state with this blue color. So this blue is gone now. Now only 2 colors are behind that we can assign to these next 5 states. So then our formula would become 2 raised power 5, only 2 colors, that's why it is 2. And raised power 5, 5 states. And 2 raised power 5, we have 32 assignments. So CSP approach is giving us this logic that you don't have to check 3 colors for all these states separately, 3 colors. No, when you are assigning blue here, then this is the neighbor of all the states, and it means that this blue is now gone, and we are only left with 2 colors, and that is red and green. So 2 raised power then 5. It is not 3. So this approach, this is the CSP basically, who is giving us this logic that we don't have to check all the assignments. So we only have to check 32 assignments. And in this way, you can see that 243 assignments were in the case of brute force, and for CSP, we only have 32 assignments. So how much reduction has been placed in your approach now? 87%. Reductions mean coming. How much work is reduced from your brute force approach to your CSP approach, how much work is reduced? 87% work is reduced. So this is the benefit of the CSP. And this is a simple example. This is a simple example, but it will give you more benefit when you will uh, when you will throw yourself into bigger problems, then you will find the real benefit of this approach. Okay, the tea is finished, and now we can continue with more concentration. So now from this simple example, we have taken the concept that by using CSP approach, definitely our work will surely will surely reduce, and it has a benefit of other normal approaches, general approaches like brute force. So the next slide uh, is an example, and this example you can read on your textbook in detail. Here, just a simple concept is being transferred, that constraints can be different types. There can be precedence constraints. There can be disjunctive constraints. So we are only understanding that what is meant by precedence constraints and what is meant by disjunctive constraints. So we only have to get these concepts. So precedence constraints, if we have to understand this, then there is an example that if you have two tasks, T1 and T2. If you have two tasks, T1 and T2, and there is a condition that either this task T1 will occur first or this T2 will occur first. So suppose if this T1 will occur first, then definitely this task T2 will occur at the second position. But this task T1 will take some time in its completion. So you have to add this time into this task. And how you can represent this whole story or the whole story into the form of a constraint mathematically, as you were mentioning earlier, SA not equal to or. So that is some kind of a mathematical notation that you were representing. Or you can say we were representing some theoretical stuff in a mathematical form. So how now this whole story of tasks T1 and T2 and T1 is taking some time, how we can represent this in mathematical form? So here, the constraint that we will introduce here for these type of things, normally called precedence constraints. So this is the form that T1 here on the slides, if you will look over these slides, T1 plus D1. D1 is the duration of that task T1 that you are going to add. That maybe it will take 1 hour or 2 hours. So this T1 plus D1 will occur first. It means that you can write less than T2. Less than T2. So T1 plus D1 less than or equal to T2. This is your representation. This is your representation. This is called precedence constraints. Similarly, for disjunctive constraints, another example is given here that if you have two axles of a vehicle that you have to install, and one axle is axle F and other axle is axle B, and those axles you have to assemble in a factory, in a vehicle, and those axles cannot overlap in time to each other. So either one comes first or the other comes first. So very much similar to the previous example of tasks, as it is mentioned in the first point, very much similar. So, but here the more focus is on either that comes first or that comes first. So in the previous example, it is mentioned that task T1 must occur before task T2. So this is the necessary condition. Task T1 must, it is a must. There is no or between T1 and T2. So T1 must occur before task T2. And the task T1 takes duration D1 to complete. So we add an arithmetic constraints of the form T1 plus T1 here, because it has to execute before task T2, so that is less than T2. And for disjunctive constraints, here we have a different condition. XLF or XLB. Either XLF can be assembled first or XLB can be assembled first. So we have the options. We don't have a condition like in previous that XLF must have to be assembled first before XLB. No. Here we can overlap. So here this condition is called disjunctive, just like disjunction operator that is available in Boolean operations. So how you can write it? How you can write it into the form of mathematics, or how you can use some mathematical notation here? This is something like that. XLF plus 10. 10 is the duration. Okay, that is not something different. So XLF plus 10 less than or equal to XLB. That is clear. That is giving this information clearly that XLF is going to be assembled first, or XLB plus 10 less than or equal to XLF. So this or is basically the disjunction. So this is disjunctive constraints. So we know that conditions it's very much close to the conditional operators available in your programming language or mathematics. This is not something different. But you are just seeing these terms in a different way. Maybe you have heard that either you can catch your ears from your right side or from your left side. So this is not a different story. So, but you are in a different subject. So you are seeing the same things, conditional operators, in a different way. So this is available in your textbook and very much easy to understand. So read it by yourself. I have just mentioned on this slide, and I am moving on to the next slide. From this slide, if you will look over the top of the slide, then the topic is changing. So the topic is variations on the CSP formalisms. Formalisms, these previous examples that you have seen, these are the formalisms. So for example, just remind your definitions in the beginning of your chapter 3 searches, when we defined some problem, or then normally we have we can rephrase this question, formalize the problem. If I say to you, then you have to do what? You have to write initial state, then you have to write the transitions, then you have to write the goal and some other things. Four or five different things that you have to mention when you want to formalize your problem. So this is the same story. So variations on the CSP formalisms. So in this topic, we will see different things. Like for example, in programming language, might be you have seen the unary operators, the binary operators, maybe the ternary. So, or maybe you have seen some. So here in this topic, we are going to see the same things like that. So the first thing is discrete variables and indiscrete. So the simple definition for discrete to you all students, because English is not our native language. So just to understand this word discrete, I am giving you a very much easy definition, or you can say desi definition. Okay, so different but unique, that is called something, that is some words to understand this word discrete. So in this discrete variable, we have to understand two concepts. First one is finite domains, and then second one is infinite domains. Finite domains, finite values, you can say. These are the domains in which you are given with finite number of values. Like you have in your map coloring example, you have only 3 colors available, that is finite values. So and also you will be given with n variables. So n variables, and if you are given with some domain size d, then you can use simple order of d raised power n complete assignment. So you can simply, so finite domains are what? In which you have finite number of variables and finite number of domain values. This is finite. And this is something in red, highlighted in red, is just an example, is just an extra, not example, but additional information, that if you have finite domains, that then you can use this simple formula to calculate your complete assignments. And complete assignment is what I told you earlier: total number of assignments. If they are legal, are consistent, then we can say it is complete assignment, total number of assignments. So how can we extract these total number of assignments? Order of d raised power m. What is this? 3 raised power 5, 2 raised power 5. This 3 is your d, values in domain, and this 5 is your number of variables in the variable set. So this is d raised power n. So this is the same thing, order of d raised power n. So for finite domains, you can use this simple formula, and then you will have your complete assignments in your hand. And the example is map coloring. And in the second point, we have the infinite domains, like set of integers that you have studied in mathematics, set of integers, and you can represent these domains with constraint languages, like you already done in previous slide. Here, this one, this is constraint language. So for infinite domains, you can use simply the constraint language, like t1 plus d1 less than or equal to t2. So this is constraint. Then is the unary constraint. So then is the unary constraints, or I can say unary operator. What is unary operator? An operator which normally takes only one operand in programming language, that is called unary operator. So unary constraint, that will take only one variable, nothing else. This is the simple definition. So unary constraint, which restricts the value of a single variable. Here it is, some example is given here, that if you are in a map coloring problem, and if some South Australians, some citizens of South Australia, if some South Australian want a green color for their state and no any other color, then this is an example of a unary constraint. How you can represent it in the form of constraint? Let's see here. Angle bracket start, angle bracket end, and we have only one variable here, SA, for South Australians, for their state, and SA not equal to green. So here South Australian don't want that green color should be assigned to them. So this constraint means this one. So this is our example. Previously, maybe I stated this example a little wrongly. So here, South Australian actually do not want a green color for their state. If you have to represent this constraint, how you can represent it? Similarly, this one, angle brackets, SA comma SA not equal to green. So this is in this scope comma relation operator, you are saying that there is only one operand, only one variable is being used and nothing else. There are not two variables or two operands here. So this is the case of unary constraint. Similarly, for binary constraint, it is very much clear now that in binary constraint, there would be two variables like SA not equal to an SW. And you have already seen in previous examples many times. So this is binary constraint. And this constraint can be higher, ternary, and so on. So for example, here, we can also describe higher order constraints. Higher order constraints, generally, a general word used for, such as, for example, maybe this is the condition that if y is between x and y, if there is some variable y is between x and y, or the value of y is between x and y. This is a constraint involving three variables and greater than binary constraints. So greater than binary, you can just represent it with higher order constraints, a general word. Otherwise, we have a word ternary for three. So it's up to you. So binary, unary, binary, and then higher order constraints. So here in this constraint, we can write between this word and then x comma y comma z. So we are basically representing this y between these variables x and y and just showing that y is between x and z. So similarly, we have some other constraints like global constraints. For example, global constraints mean you don't know, so the number of variables could be any arbitrary number of variables. So then it is called global constraint. And one most common global constraint is simply all diff. For example, in mathematics, for every, there is a notation for every. So that is something global. So all diff means all the variables involved in that, in some problem, have different values. So now we are going to see an example of this constraints, particularly all diff, global constraint. Rest of the constraint maybe you have seen in your programming languages and in some other courses many times. But here we are going to see global constraint deeply. An example of this global constraint is crypt-arithmetic puzzles or crypto-arithmetic. Some people say crypto-arithmetic puzzles. And now we are going to, so crypt-arithmetic puzzle is an example of this global constraint all diff. And in crypt-arithmetic puzzle, we will see from the next slide here on, that is, in this puzzle, we will be given some letters or strings, like for example this way, plays plus well is equal to battle. So we will be given with these kinds of strings. This is just one example. These strings can be different. So we have to sum up those strings. In this puzzle, there are two strings given to us, and these two strings we have to sum it up, and we are getting this string better as a result of these two strings. So this is the input that would be given to us for this problem, crypto-arithmetic problem. What we have to do, we have to replace these alphabets. We have to replace these alphabets or letters with numbers from 0 to 9. With numbers from 0 to 9. We have to replace these numbers. And there are some constraints that we have to follow, and we will see those constraints. So the first thing that we are given with some strings, and this is the problem of addition only. It can be multiplication, subtraction, whatever, but at the moment we are considering only addition. So, and then what we have to do, we are given with only 0 to 9 digits, 0, 1, 2, 3, and up to 9, and we have to replace these letters in the strings with the numbers, and each letter. So first constraint is I can use only 0 to 9 digits. Second constraint is that it's gone from my head. So we will see when it will come again. So after replacing, yes, it is coming into my head again, sorry. So first thing, 0 to 9 digits, and then each letter in this problem, each letter, we have to assign unique numbers to these unique letters, you can say. If I am assigning number 8 to this P, then this, whenever this P will occur in these strings, that would be represented with 8. And we cannot assign this number 8 to any other letter. For example, to L, I cannot assign 8 to L or E or anything else. It is finished now. It is now done. We have already assigned this 8 to P, and now we cannot assign this 8 to any other number. So this is also a constraint. So keep these constraints in your mind, and maybe if some more constraints will come within our discussion, then I will tell you. So this is now our puzzle. We will be given with the string in this form, and then we have to find the numbers. And after, yes, there is another constraint, that after replacing all the letters with the numbers, you have to check that this summation, the result of this summation would be accurate with the numbers that you replaced here. This is also a constraint. So for example, here you are seeing, for example, you replaced P with 9, you replaced L with 7, and here this is L, double L, and here you are seeing double 7. And for example, A is here, A is not at any other position. So let's see. For example, I can use annotation also here, if it will. Yes. Just a minute. Yes. So for example, this, I am saying this 9, and P is not anywhere else. So now L is this 7, and this 7 is gone here. This 7 is also going here, and there is no any other. Y is not repeated. Maybe E. E is what? E is your this 0, huh? So E is this 0. Maybe I can change the color, and then it will give you more understanding. So for example, this is E, and E, sorry, and here you can say, I can just represent, this is again 0, and here this is again 0, and this is also the same positions here. So what I want to say, that if you used some number for a letter, then you have to repeat that number at every position where that letter is coming again in the strings. That's simple. It seems that I am making the things more complex now. So just leave these things here. So let's move on. So it is mentioned here, each unique alphabet represents a unique digit, unique alphabet, unique digit, and from 0 to 9. So if we will found a solution for this string, then that would be like this one. And now we are going to see some other things. Okay. So the basic rules, it's just a repetition. We have seen these things already. What are the basic rules? Highlighted in red. Each unique digit from 0 to 9 must be replaced by a unique character, or vice versa. You can say each unique character must be replaced with a unique digit 0 to 9. So one other point which is coming into our mind, that we can give you the numbers, and then I can ask you, you have to replace it with letters, and then letters would be from 0 to 26. Then the domain would be wider, but leave it. So anyhow, you can just I should have to change this slide. Just wait. Maybe it's each unique character must be replaced with unique digit from 0 to 9. So this is basically the true understanding. Each unique character must be replaced with unique digit. Okay. And the number so formed cannot start with 0. This is not basically the rule. This is just a restriction for our easiness, or for our ease. Because otherwise we have to think too much. If the number can start with 1 also, what it means? It means, for example, this number, the resultant number, this is starting with 1. Okay? So this is saying that number cannot start with 0, which means that this bit on the left hand side of this string, or of these numbers, cannot be 0. So this was the second rule. And this is not basically the rule, as I said. This is just a restriction to make our computation in this problem, just to make our computation easy. So, and the example is, for us, the example is send plus more is equal to money. This is our strings are now. And we can write these strings like this way: send plus more is equal to money. And here you can see D plus E you have to add, and maybe if some carry will occur. And if there is some carry, then that carry will go to the next portion. That is why it is mentioned A here. And when you will add this A and or, you will get some value here. But it is quite possible that you will get some carry here, and that carry is moving to the next portion. So here D plus E plus Y. Here you can see D plus E is equal to this Y and this 10A. When your value is greater than 10, for example 12, then it is 10 multiplied with that carry, which means that there is one portion of 10th is available here. So here you have to move the carry to the next part. So, and D, for example, this is the normal equation. Here, normal equation for summation. Here D plus E is equal to 10A plus Y. This is the normal mathematical equation for the addition. For example, if you have 12 here for Y, and if you have 12, then what is the carry? Carry is 1. So when carry is 1, the 10 multiplied with that 1, you will have 10 here. And now this y is 2. You have to write 2 here, and so 10 plus 2 is equal to 12. And that is the answer of summing up D plus C. Hope you will understand this equation. So this is the normal mathematical equation for addition. So D plus C is equal to 10A plus Y. This is not necessary for the solution of this problem, but if you will have this knowledge, then you can use this knowledge to find your solution quickly and speedily. This is the advantage of mathematics that you have in your mind already, that you have in your head already. Anyhow, so then the next one, A plus N plus R. Similarly, A plus N plus R here is equal to 10B, next one, plus E. And now you hope, and if after adding these values, if you are getting 15, then A, N, and R. After summing up A, N, and R, you are getting 15. So this right-hand side here is equal to 15. You have to write 5 here in place of E. So 5 here in place of E. And then you can, what is carry? 1. That you have to multiply with this 10. 10 multiplied by 1, 10. So I hope you understand it is not a difficult thing, but if you are feeling some kind of difficulty, then I can explain on the simple small board. I don't know, but I hope that you are understanding, but maybe some of the students are not getting the point. So for example, this is something, send plus more is equal to money. Okay, and this is your carry A, B, C, and maybe the M. What I am saying initially, for example, I am going to explain this part, A plus N plus R plus E. And on the slides, I hope you are also seeing, I can stop sharing the slides. So I don't know what to have to do. Maybe I can stop sharing, then this video, this board will be highlighted. Okay, yeah. It's so this, if you will sum up this one, D plus E is equal to 10E plus Y. This is the formula for the addition. For example, these values are 8 and 7, and you are getting 15 here. And it means that you have to write 5 here in place of Y, and 1 is the carry. So 5 here plus Y, and this is equal to 1. So 10 multiplied by 1, this is just a simple representation. And 10 multiplied by 1, 10 plus 5 is equal to 15, which is equivalent to this value, which I am going to explain. And similar is the case here. Now similar is the case here. For example, now A plus this one, A plus N plus R is equal to 10E plus E. A plus N plus R is equal to 10. This is 10, and the next carry 10B plus this one E. And now hope you will understand. And if after summing these values in an addition problem, if after summing these values, if you are getting 19, then you have to write 9 here, and 1 is the carry that you have to move to the next portion in an addition problem. So this is the 10, and the next carry plus E is your 9 here. So that is equal to 19 actually. So this is not something different. It's quite simple problem of second class or third grade or second grade actually. So don't worry. So now I hope you have the understanding now. And now I can share the screen again. So now you are seeing this B plus E plus O is equal to 10C plus N here. And similarly, C plus S plus M is equal to 10M plus this O. So these are the equations of these four portions that you have to do for the solution of this problem. So you have to keep these equations in your mind. And now we have not started the solution yet. Yes, this is something that you have to keep in your mind. We have not started the solution of this problem yet. We are just getting the understanding first that how much calculations that you have to do or how you have to solve this problem. We will start the solution for this problem from here or from this slide. Anyhow, so now in this problem we have 10 digits, 0 to 9, 10 digits. We have 10 digits. We have 8 letters, 1, 2, 3, 4, 5. This is repeated. 6, repeated, repeated. 7, repeated, repeated, and 8. We have 8 letters. 2 carry digits. By the way, we have 4 carries here, but 2 carry digits mean the value of the carry could be either 0 or 1 and not more than that. So these are the normal carry values that we have in an addition problem. So 2 carry digits, 0 and 1, and 4 carries involved, A, B, C, and M. 4 carries for this problem, send more plus money. So now you can use this equation and you can compute that how many total number of candidate solutions or assignments that you have to compute. So 10 is the digit, total of 0 to 9. 8 is the letter, 10 raised power 8. 10 is the values that you have to assign. And 8 is the letters set of variables. So 10 raised power 8 multiplied by 2 is the carry values. And 4 are the carries multiplied by 2 raised power 4. So these are 2 is the values of the carries. And how many carries, how many variables? 4. So then 10 raised power 8 multiplied by 2 raised power 8, you will have, oh, I cannot pronounce this value. So I cannot pronounce this value. So this is the total number of assignments that you have to check. So I cannot pronounce this value. Oh. Oh. So, however, if we will focus on this restriction that the number so formed cannot start with 0. So it means that the starting number, this one, M, this should not be 0. It should be, and this is a carry. So this is a carry, and the problem itself saying that it cannot be 0. So then what would be the value for them? Only one value is remaining, that is 1. If it is carry, and carry can carry can carry 2 values, either 0 or 1. And the problem itself is saying that there is no 0 value for the starting number. For the M actually, there is no 0. So then what would the value remaining? The value is only 1. So the problem itself saying that M would be 1. And if M would be 1, then among these possibilities, half of the possibilities are finished. Those possibilities will have zeros in position of this M. So then we are only living with this maybe this is 80 million and this is something 160 million. I don't know, maybe I am wrong. So this is only 80 million. So with this restriction, we only have to check with, so this is constraint satisfaction problem, CSP. Otherwise you have to check 160 million entries are the candidate solutions. But here with this restriction, with this constraint, you only have to check uh, 80 million candidate solutions. So I am taking a little break here and then I will start it again. Just wait. Okay, let's start it again. We were here at this slide and we have already taken the understanding of these equations mentioned here or at the bottom of this slide. And now we will have to move on. So this is your actual starting of the CSP formalism. And here you are seeing that we are writing this send plus more is equal to money again. And we are mentioning some carries A, B, C, and M which are involved in this solution. And from our set of constraints, we already know that this M, which is the start of this number, resultant string. So this would be 1 as it is given in the constraint here. The number so formed cannot start with 0. This is the restriction given here in the constraint set. So that is, you have to mention that M is equal to 1. So after this one, the next possibility that you have to think that this M is 1 now. You can mention this M with number 1. Here M is 1. Here M is also 1. And here M is also 1. This M at these positions, you should have to mention with 1. And I can also use this annotation. So this is 1. This is also 1. And this is also 1. So after putting the value 1 for M in our CSP, we have this state now. This is your next state. And the next possibility that you have to think is, if you want to solve this CSP, you have to think in this way, that you have to think in that what would be the value for these carries. And at the moment, or up to this state, we have evolved that the letter M, which is in our CSP, has the value 1 according to our constraint set. Next, that we have to think that what would be the value of this C. The value of this C would be either 0 or 1. This is either 0 and this is either C is equal to 1. So you have to think in the form of a tree to solve some problem. Or you have to think in the form of some conditions or constraints. So when you are considering that the value for the next carry C is, for example, 0, then this is on the left hand side. And if you are considering that for example, C is 0, then what is the possibility? Then you have to think here. if you will place, so 0 plus 1 is equal to 1. So only S is remaining. If you will place, so the equation for this one is 0 plus S plus 1 is equal to 10M plus O, and the M is 1, so it is 10. After putting these values, we will have S plus 1. This 0 is now finished. 0 means 0. So S plus 1 is equal to O plus 10. This 10 is coming after multiplying with M, and M is 1. So 10 multiplied with 1, we have 10. So if you will put 9 here, so 9 plus 1, you will get what? I will get 10. And then I can write 0 here and 1 as a carry to the next digit, which is satisfying your constraint. So it means that I can put the value of S as a 9 here. I can. But now think, if you will put the value 8 into this variable S, then 8 plus 1 is equal to 9, and we will have carry 0. So it means 8 is not feasible. 8 is not feasible are the values less than 8, even 7, 6, 5, 4, 3. They are not feasible. Only 9 is feasible. Only 9 is feasible and satisfying our constraints. So when you will put 9 here in place of this S, then 9 plus 1 is equal to 10, and the value of S will be 9, and the value of O will become 0, and then 1 will go on as a carry to the next, and all the constraints are satisfying. So here we have S is equal to O plus 9, 10 minus 1, this 9. So that's why it is written here, S is equal to 9 and O is equal to 0. That you have to conclude, as I have concluded before you, that after putting the value 9 to this S, we will have the situation like this. So this is for when you are considering carry C as a 0. And now on the other hand, when you are considering your carry C as 1, this is another case. If you are considering this C as a 1, then 1 plus 1 is equal to 2. And if you will put S as a 9, so 9 plus 1, it is 11, then O will become 1, and 1 will go on further, and you are going to give this O value 1, which is not possible because you are already giving this 1 to this letter M, and now you are getting O also as a 1. So this is not feasible, and this is violating your constraint. So 9 is not a good value in case when C is 1. So however, when you will put 8 here, then 8 plus 9 and this one plus 10, then you will have O as a 0, and carry 1 will move on to the next part. So then it is satisfying. Then it is satisfying. Forget it, because this is something on the other hand. Either you can move on this side, or either you can move on this side. So here it is written 1 plus S plus 1 is equal to 10 if you have a carry 1 moving to the next part. So that is 10 plus O. So S is equal to 8 plus O, which means that you can, if you will put 8 here, then you will have the value for the S as a 8, and the value for the O as a 0. Okay, 9 is not feasible in this case. 8 is feasible, but keep now the value of S as 7. So 7 plus 1, 8, and then C 9, then O will have 9 and carry 0, which is again violating the constraint. So when you will put the value of S as a 8, then it is feasible, and the value of O will be 0, and the next constraint is also satisfying. So this is that case. So we can also move on to this part also. But when you will evaluate it further, maybe in the next portions, you will get some wrong results. So anyhow, I can go on to those concepts, but I am leaving these further steps. Uh, I am leaving these steps for you. You can uh, evaluate, you can calculate these steps by yourself, and you will see that in the next steps you will again stuck. Anyhow, but there is also a possibility that you will get some solution here also. But then your final solution will be different. That is also a possibility. A problem can have multiple solutions. That is something we already know. But here we are going in this direction. So, and in this direction, at the moment, for M, we have the value 1. For S, we have the value 9. And for O, we have the value 0 according to our calculation. Now, move to the next step, that now we will think for the next carry, which is B. So let's move on to the next point. So next is when carry can be, we are now we have to think with respect to this carry B, and we are here at this point. Either carry can be B is equal to 0, either carry can be B is equal to 1. So now we are thinking, so we are putting this carry C as a 0 in this case from the previous part of the tree. And now if B is 0, then what will happen? And when B will be 1, then what will happen? We will see on the next slide. You can have a look here before going on to the next slide, because M is 1, O is 0, S is 9. So you can put these values here. When B is 0, M is 1, O is 0, S is 9. This is M, and this carry C is 0. And now we are putting this carry B 0 according to our assumption here. According to our assumption here. I can also use annotation. So after putting this value of B as a 0 here, we have this situation 0, and we can also just move on, just look on the previous slides. So this is O also. So this O is 0. So I can put 0 wherever this O occurs, this letter O occurs. So I am also putting 0 here and under this column of B plus E in the next slide. So here you are seeing this 0 is here in place of O. So 0 is for B, 0 plus E plus this O. So E plus 0 plus 0, E plus 0 plus 0 is equal to N plus 10 multiplied by the next carry, which is 0. So 10 multiplied by 0 is 0. So that's why it is N plus 0. And here we have finally E is equal to N, which means the value of letter E and the value of letter N is same, are equal, which is wrong, which is violating our constraints. Because in our constraint set, we know that each letter must have different value. So this is something invalid, not valid. So we have to stop here. So this is the dead end. So it is dead end. So we have to continue with B is equal to 1. Okay. If B is equal to 1, then we can put this B is equal to 1 here, and E and 0, and rest of the values that are mentioned here, these are the final values. These values are already done by us. So 1 plus E plus 0, or E plus 0 plus 1, you can write in any way, and then it is equal to 10 multiplied by the next carry, which is 0, and so it is N plus 0. And we are getting E is equal to N and minus 1. after simplifying this equation. So this is saying that E is equal to N, but you have to minus something from N, then you can say E is equal to N minus 1. For example, if E is equal to 6, then N is equal to 7 minus 1. So then the value of N would be 7, and after subtracting it with minus 1, then we will have 6 is equal to 6. So this is something good. This is not violating our constraints. So this equation is giving us a clue that it is okay, and this is not violating our constraints. So we don't have any value yet, but this equation is feasible. This equation is not violating any constraints, and in future we can use this value to extract we can use this equation to extract the value for the E or the N. So okay, we will keep this equation with us, and now the next portion is just the remaining carry A, which can be 0 or which can be 1, as you are seeing. This is the case when A is 0, and this is the case when A is 1. So okay, up to this point we don't have find. Up to this point we do not have find any value for E or N, but we have found some equation that can be helpful in future calculation. So okay, we can go on. So by putting A is equal to 0 in our CSP, okay, A is 0, and then we have this N and R and E, very much similar to the previous state. And now we have 0 plus N plus R. 0 plus N plus R is equal to 10, and we have the carry 1. Here in this case we have the carry 1. So 10 multiplied by 1, we have 10. 10 plus E, and this E is coming here, 10 plus E. So N plus R is equal to 10, and we can put this E is equal to N minus 1 here in this equation. So we can replace this E with N minus 1 here, and then we can cross this N with this N, and finally we will have R is equal to 9 value. Here in this tree, we already have 9 value for S. We already have 9 value for S, and we are now getting R is equal to 9, which is not good, which is violating our constraints. So that's why it is invalid. So we have to focus on the right side, where A is equal to 1. So when carry A is equal to 1, then you have to put 1 again in place of A. So here it is 1, and then N, R, and rest of the problem. And you can write it here, 1 plus N plus R. 1 plus N plus R is equal to E, and next carry is 1, so it is E plus 10. So 10 multiplied with this next carry, I will get 10. So 10 plus E, that's why it is E plus 10. So now N plus R is equal to E plus 9. And you can just subtract this 1 from this 10, and you will have E plus 9. And N plus R is, now we have this E. So we can use this equation here again, because we have N on the right hand side, and if we will replace this E with N minus 1, then we can simplify this equation further. That's why we are replacing this E with N minus 1 with N minus 1 we are getting from this equation. Okay, so here after simplifying this equation, we will have the value for R as is equal to 8, and we don't have this 8 assigned to any alphabet earlier. So here, if we are getting R is equal to 8, then it's okay, because this is something new value, and this is not already assigned to any variable. So that is okay. So now we can put the value 8 in place of this R. In place of this R. Okay. So this slide is now, I hope that it is clear. So now we are moving on. So now we are just putting the values that we have concluded up to this state. So our M is 1, okay. Our carry C is 0, S is 9, M is 1, O is 0, here O is 0, this B is 1. If you will look over here, this B is 1, this B and this A is 1. When we were following this part of the tree, we will have A and B as 1. So this is the reason that this B is 1, this A is 1, and now we have this R as 8. And rest of the variables, we don't have the value for these variables or letters or alphabets yet. We will find these values. So we are basically doing what? We are solving the puzzle. And what is that puzzle? The puzzle is Crypt-arithmetic puzzle. So, and up to this point, we have the value 8 for the alphabet R. We have the value 1 for M. We have the value 0 for O. We have the value 9 for S. Yes. Now think that value 9 is gone. Value 8 is gone. Value 1 is gone. Is there any other value? 9, 8 are gone. 0 is also gone. Yes, 9, 8, 0 are gone, which means that they are already assigned to some alphabets. So what are the remaining letters? 7, 6, 4, 3, 2, 1. Sorry, 1 is not. 1 is assigned to M. So 7, 6, 5, 4, 3, and 2. 0 and 1 are already assigned. So now what we can do now? So now you have to, all our options to evaluate or conclude some values up to this state of the problem, all our options are now finished. And now what will be the next step, or what will be the next step that we can adopt, and then that through which we can extract further are the remaining values. So the next approach is simply the brute force approach. You can just try one value and then you will infer that what is the effect of that value to the whole problem. And in this way you can go on and go on up to the end of the problem, and if you are not violating any constraint, then you will have finally all your values in your hand, and then you can say, okay, this is the solution, and you can have it. So these points are just mentioning that brute force approach. I can, for example, I can assign this E the value 7. After assigning this value 7, 7 and 1, for example, 7 and 1, 8, and then then the n would have the value 8, which is not good because 8 is already assigned to R. So 7 for E is not a good option. Okay, then what is next? I can assign 6 to E. If you assign 6 plus 1, 7, then n is 7, okay? At the moment it is fine. So n is 7 and E is 6, okay? So when you will put this n, so I can use annotation so that you will not forget. So I am saying that, okay, I am writing this E as a 6, and what I am getting for n, I am getting 6 plus 1, 7. And now when you will put 7 here in place of this n, 7 plus 1, 8, 8 and 8, 16. And then you are getting 6 for E, which is, okay, E is 6, E is 6, that is fine. N is 7, okay, that is also fine. So here, this one, so 8 and 8, 16, you are getting 6 and you are getting this carry next word, next. So the constraints are satisfying. And for example, in previous step, 6 plus 1, 7, and 7 is here and 0 is the carry, constraints are satisfying. So up to this point, this is okay. if you will put the value of E6, then all the things are going fine. But this last column is still remaining. So E is 6 now. E is 6 and N is 7. So, and now you have to put some values for D and Y. So up to this point, I can write, for example, yes, I can show you on the board so that we can move on quickly rather than this annotation tool is handy but not speedy. So that's why I can use this board. And first I am going to write the all numbers. So we have this situation that 1 0 1 1, and then we have 9 E N and D, and then we have 1 0 8 and E, and then we have 1 0 N E and Y. So this is the slide, and we have M is equal to 1. Just a moment, I can stop it and I can stop sharing, and I can, so that you can see it in a bigger way. So this is the situation on that slide. So M is equal to 1, and this was S is equal to 9, O is equal to 0, this one. And if I will put E is equal to 6 here, so then 6 plus 1 7, so I will get N is equal to 7 here. 6 plus 1 7, so I will get N 7 here, which I have written here. So then 7 plus 1 8, 8 and 8 16, so I will get 6 here and 1 as a carry, so all the values are satisfying, so that's good. So okay, now E is what? I can place some value here. E is 6. Now this E is 6. And now I have to extract values for D and Y. And how many values? 9 is gone. Also there is R. R is equal to 8. R is equal to 8 is also gone. So how many numbers are already gone? 9, 8, 7, 6 are gone. What are the remaining numbers? 5, 4, 3, 2 are remaining. 5, 5, 4, 3, 2 are remaining. 0 and 1 are also gone. So now I can put these remaining numbers for D and Y, and I can check that either I am going in the right direction or not. So first put this D as 5. E is 6. E is 6. So 6 plus 5 is equal to 11. And for Y, it is 1 is coming, which is not good because I have 1 already for M. So 5 is not a good option for D. So 5 is not a good option for D. So then you have to put 4. 4 plus 6, you will get 10, and Y is now 0, which is also not 0 because we already have 0. So 4 is not a good option. 3, you can put 3 for D. 3 plus 6 is equal to 9, You will have the value 9 for Y, which is not good because 9 is already there. So 3 is not a good option. So then you can check 2. 2 plus 6, 8. Then you will have 8 for this Y, which is not good because it is already done. So this 2 is also not a good option. So it means no any number which is remaining, no any number is helping us in finding the solution. It means that our supposition here, when we supposed E as E is equal to 6, is not good. Is not good. Now you have to change the whole process. And now you can see that whole your hard work is now 0. So, okay. So what you have to do, E is equal to 6 is not a good option. So I can write r is equal to 8. So we are at the position of 8, and I can remove all these other things. So now what I can do, I have checked 7 for E, I have checked 6 for E, and I am not finding a solution. So what is remaining then? Then my next option is, now I'm going to check 5 for E. So 5 for E. When I will put 5, this E, so 5 plus, when I will put E is equal to 5. So 5 plus 1 is equal to 6, and I will get 6 for this N. So okay, I am getting something. We 6, and the carry is 0 next because it is 6. So this is okay. And then now you can put this and 6 plus 1, 7, 7 and 8, 15. So I am getting 5 for E, and 1 is going on as a carry. So this is satisfying. This 5 is also equal to the previous value that I have supposed. Okay, now again, now here, now 9, 8 are gone. 7 is remaining. 6, 5 are gone. So 4, 3, and 2 are remaining. 0 and 1 are already 0 and 1 are already finished. So 7, 4, 3, 2. Now you have to check it. So when you will suppose D as a 7, and so now my E is 5. So now my E is 5. So 7 plus 5. So when I am supposing D as a 7, 7 plus 5, 12. So I am getting 2 for the Y, and 1 carry is moving forward. So that is satisfying. So from this supposition, everything is going on, and that is satisfying. So 2 is not, for example, assigned to any other number before. This 7 is not already assigned to any number before. Okay. So for 7, it is a good. You can check the rest of the numbers, but I am not going to check it. You can check it by yourself. For example, 4 plus 5, 9. Then you are assigning 9 to this Y, and 9 you already have. So you will face some music. So leave it there. So I am just taking this 7, which I have supposed, and it is not violating any constraint or any condition. So I am going with this one because I have my solutions now. So now my D is 7, which I have supposed. So now my D is 7, and E is 5, and is 6, and now my Y is 2. And I think I have done with all the numbers. So now I can just 1, 0, 1, 1. I can write my equations again, and 9, and this is 5, this is 5, this is 7. Oh, sorry. N is 6. N is 6. D is 7. And then 1, 0, 8, and E is 5. And then 1, 0, N is what? 6. And E is what? 5. And Y is what? 2. So this is what I have done. So I am checking it again. E is 5. Okay, E is 5. This E 5. N is what? 6. So N is 6. And where the other N? This is the place of N. 106. Okay, this is N. So 7. So 7 plus 5, 2, 12. And 1 is going as a carry. So 8 plus 16, 14, 15. 5 is there, and 1 is going on a carry. So 5 plus 1, 6. 6 is here. 9 plus 1, 0. And 1 is moving on as a carry. So this is the sum. So sum is also okay. And I have the unique digits for all the alphabets that were given in our puzzle. So now my puzzle is solved. So now I am moving to my slides, and I'm sharing my slides again. And I'm leaving this small smart board. This is actually the smart board. So, okay. So I hope that you are now seeing the slide. So when we will have E as 5, then by using this equation, you can conclude the value for n, or you can put this value E in this problem as I did, and then you can infer the values by yourself. So if you will put this 5 in that equation, E is equal to n minus 5, then n is equal to 6. And putting these values we have, and then you can check all the values one by one as I did, and then you will have the value of y as 2 and the value of d as 7, and finally you will have the values for all the variables, and then you can write your solution in this form. And we already checked that the sum of the solution is also perfect, okay. And now we have the values, the numbers for all the unique letters. We have found the unique numbers for all the unique letters that was given in the problem, and the constraints of all the columns in addition and all the constraints given in the problem are also satisfying. So I hope you have enjoyed or you will enjoy this part of the lecture if you have something in your head. So I am stopping myself here. I am taking a break. Half of the lecture is remaining that I will continue in the next lecture. So I will start from this backtracking, inshallah, from the next lecture. So until then, bye-bye.